we created a PID controller where instead of using an SMU to measure the speed of the motor, we created a mechanical system where you can measure the speed of the motor using a second generator that was connected to the motor via a linked axle.
This ends up making it significantly easier to get a speed reading because, well, you're not putting any current through the second motor, and the load across it is extremely small because we only want to measure the voltage that's produced by it. Therefore, we can basically assume that the voltage across the motor is the voltage across the motor.
So over the course of our project, we slowly created first the motor generator pair system, where we're able to measure the speed of the first motor using the output of the generator. And then we created a filtering system that would allow us to filter down the mechanical noise of the motor data.
As we saw in all three of the motor labs, motors tend to be much less clean than electrical signals, at least the motors that we were dealing with. So we ran them through a couple of low-pass filters, both at very low frequencies, right around 10 to 20 hertz, to filter out basic modulations caused by the coils in the motor.
We then moved on to create a difference amplifier, which we used, and a set point, a variable set point with a voltage follower after it to create to sum the difference of the set point in the data, the speed data we were getting.
This allowed us to get an error metric, a measurement of how far away from where we wanted to be. It let us basically pick a speed that we wanted to spin at and have an analog signal that tells us how far from that speed we are.
Then we're going to enter the three parts of our PID controller. The first being the proportional control system. Proportional control works by using multiplying a set point of the error between the speed reading and a set point by proportional control to try and reach the set point. The issue there is that losses cause a steady state error so that the speed will never actually reach the set point.
This is solved by adding in an integral control, which integrates the area left between the set point and the error. The set point and the speed, which is the error. This allows you to get rid of the steady state error. However, it turns the system into a second order system and has the unintended consequence of creating ringing, where the actual voltage goes back and forth around your set point.
To mitigate this hunting problem, we also implemented a derivative control, which would take the derivative of the change in the error, and then that was able to basically eliminate the overhunting problem.
Ready?
Yeah. Go ahead. There we go.
So the real purpose of a circuit like this, I mean, PID control is used in a lot of different applications. The real purpose is it gives you the ability to have feedback that drives the system such that you can control it very precisely.
Or you mean multimeter. Look how fast this thing's going still.
Good.
In a lot of systems that are fragile, if you have too much hunting, then you can permanently damage the system. If you don't reach a set point, then the amount of error is unacceptable.
It allows you to create a very custom tailored response for the specific system.